Hello everyone, and thanks for watching Edupedia World Videos. The previous video was about work, and this video we'll discuss concepts of energy. So let's take a brief recap of what we learned previously. We defined a differential or a small amount of work as the dot product of the force and the small displacement. Now, this force is the resultant force, so the work done is the net work done. If we wanted to find the work done by an individual force, we would take this to be the individual force instead of the total force. We also defined kinetic energy, which is often abbreviated as K, and it was defined as half mv square, and it is the energy of a particle due to motion. So we can see from the formula, a particle at rest has zero kinetic energy. The larger the speed of the particle, the more kinetic energy it has, right? And also we derived a nice relationship between them. So let's see that briefly. Kinetic energy is half mv squared, right? dW is f dot dr, which for one dimensions I can write it as f dx, which can be written as ma dx because f is equal to ma, and a is equal to v dv by dx, so it can be written as mv dv because dx and dx will cancel, right? Now if we integrate these two, integrate just means addition, right? And we want to find out the total work. We see that W is equal to half m v2 squared minus half m v1 squared. We don't need a constant of integration because we are doing definite integration right now. We have the limits, right? The initial speed was v1, the final speed was v2, which means W is equal to k2 minus k1. This is a very important result, which is known as the work energy theorem. So if we do a positive amount of work on a body, its kinetic energy will increase. If we do a negative amount of work on a body, the kinetic energy will decrease, right? This is valid for a single particle, right? By the way, we'll not talk about extended objects till we reach rotational mechanics, but let me just tell you the difference between them. Let's say this is a box. It is an extended object. When I say I apply a force of 10 newtons towards the right, that does not give me a lot of information. Actually, let's make it three-dimensional to make it more realistic. That doesn't give me a lot of information because I could apply a force of 10 newtons at this corner or at this corner or at the midpoint of this side, and they would give me slightly different motion, right? So it is not just enough to tell the direction and magnitude of force. You have to tell where the force is acting, because this itself is an extended object which has dimensions. It has a certain length, breadth and height. As opposed to that, this is a particle. A particle has no linear dimensions. When I say a force of 10 newtons is applied towards the right, you can be sure that this is the force, and I've told you everything you need to know about the force, right? So this work energy theorem is valid for a single particle. Let's see what happens when we have more than one particle, right? So let's say this is a particle of mass m1, this is a particle of mass m2, right? And let's say they both exert a force towards each other, attractive force, let's say, of magnitude F. It could be the gravitational force, for example, right? And no other force is acting on the particle. Now, if I ask you the net acceleration of the system, that right now we cannot do. We'll be able to do it later on. But now remember that when we did Newton's laws of motion, we said that we can only consider systems which have the same acceleration. So these two together cannot be considered as a system for the purposes of Newton's laws of motion yet, right? But we know that if we add these two forces, we will get zero, because this is a force F towards the right and this is a force F towards the left. So they add up to give me zero, right? However, let's say due to this force, and these two have to be opposite because of Newton's third law. Let's say this particle moves towards the right a distance dx1, and this moves towards the left a distance dx2. So what is the work done on this object? That is f dx1, and on this object it is f dx2. So we are not applying Newton's law right now, we are applying energy conservation, and for that purposes we'll take these two things together to be a system. So the net work done on it is f dx1 plus f dx2. right? And that is not 0, right? Though the forces are opposite and hence they add up to 0, the displacements are opposite. So when you take the dot product of the force and displacement, in both cases they are positive. For m1, the displacement is in the direction of the force, so work done is positive. For m2, the displacement is in the direction of the force, so work done is positive, right? And these two, for this system, would be considered an internal force. Right, so let's say you have 10 particles in a system, then the forces which those 10 particles apply on each other are internal forces, and any external force you apply will obviously be called an external force, right? So this is an internal force. So we see a very important result, which is that even though the sum of internal forces is always 0 by Newton's third law, the sum of the work done by internal forces does not need to be 0. In other words, internal forces can do work. And we can see from our common sense that if we leave these two objects that attract each other, they'll move towards each other and their speeds will increase. So the internal forces will be doing a positive amount of work, this much, and hence their kinetic energy will start increasing. Let's see that quantitatively. Right. So F dx1 plus F dx2 is the total amount of work done. Right. We can also write it as m1 a1 dx1 plus m2 a2 dx2. I'll do the same thing I did previously. So this can also be written as m1 v1 dv1 plus m2 v2 dv2. This is equal to dw, right? The differential amount of work done by internal forces. We integrate them. Let's say v1 was initially at v1 naught, v1 initial rather, and finally it is at v1 final, and v2 was at v2 initial, and then it became v2 final, right? So from that we get w is equal to, I'm just going to write it like this, k1 final minus k1 initial plus k2 final minus k2 initial. That is equal to k1 plus k2 finally minus k1 plus k2 initial. Right, this is the work done. So we see an important result. For one particle, the work done by external forces, remember, for one particle there can be no internal forces, right? Because it's a particle. If you have an extended object like the cube we saw earlier, how does a solid stay together? All the molecules attract each other, right? They exert internal forces on it. Of course, the sum of these internal forces is 0 because they cancel in pairs by Newton's third law. But in this case, if the body is like this, they're not doing any work, right? But for a single particle, it makes no sense to have internal forces, right? So work done on one particle, which is obviously the work done by an external force, equals the change in its kinetic energy. For a system, the work done by external and internal forces equals the change in kinetic energy, right? So we never took internal forces into account in Newton's laws because they always add up to 0. But when we talk about the work done by internal forces, that need not be 0. We saw in this case, internal forces did some positive amount of work, and due to that, the kinetic energy of the system increased, right? Let's move. Now, the thing is, we can solve basically any problem of conservation of energy like this using particles, in which we'll say we'll calculate the work done by the external forces and we'll calculate the work done by the internal forces. We'll add them up, and that will be equal to, that will be equal to the change in kinetic energy. But generally, the work done by internal forces is not very convenient to work with. So instead, we define a new term which you've probably heard before, and it is called potential energy. Right. So let me just write down here what we've done till now. For one particle, W was equal to K2 minus K1. I apologize for using these inconsistent symbols. Earlier I used I and F. So now I'm using 2 and 1 because 1 was the initial and 2 was the final. Right. And for a system of particles, W external plus W internal is equal to K2 minus K1. In this, K2 is the kinetic energy of one particle. In this case, K2 is the kinetic energy of the whole system. That is the sum of the kinetic energy of individual particles. Right, so this is for one particle, this is for a system of many particles. Now, we are focusing on W internal, work internal. That's generally not easy to work with. So, instead of that, we'll define something else called potential energy. So, the definition of potential energy is this. I'm going to write it down and then I'm going to explain it. Change in U. And potential energy, just like kinetic energy is abbreviated by K, potential energy is generally abbreviated by U. Change in U, right? That is, this would be the change in K, right? K2 minus K1. So this is basically final potential energy minus initial potential energy. Change in potential energy is equal to the negative of the work done by the internal forces, right? So that's it. We define a potential energy, and the change in potential energy is the negative of the work done. So let's say we have a system of two particles. I'm going to keep this one stationary. I'm going to move this one. This one initially was at position I and finally is at position F. Right. And for now we'll assume that there is no external force. Right now we're just focusing on the internal force. So let's say this particle exerts a force F, variable, it can change with position. I'm just going to draw it like this. The particle exerts a force F on the second particle, right? So the change in U will be written as U final minus U initial. By the way, just like kinetic energy is by virtue of motion, potential energy is by virtue of or due to configuration. Configuration just is another word, is a fancy word for saying position. So this is one configuration of the system, right? Where this particle is at this point, this is at this point. This would be another configuration of the system, right? So two different configurations, two different potential energies, right? So U final minus U initial will be equal to the negative of the work done by the internal force on this object. So let's say it moves from I to F, the work done will be F dot dr. Right, now F might be changing with position and dr is the small differential displacement. So we take the small amounts of work done in these small intervals by this force and we add it all up, right? But what is integral I to F, F dot dr? That is, now just look at the right particle for a moment. Now we are not taking them both as a system for a second. We'll just take the second one as a system. On the second one, we assume that no external forces are acting. So F is the only force acting on this one. F dot dr is the work done by this force in taking it from the initial point to the final point, right? But by applying the work energy theorem for this single particle, this first one, we can see that this is equal to negative of K2 minus K1, right? Again, I actually apologize for this. I'm just going to call this U2 minus U1, right? The thing is, both these conventions are used and it does get a little bit confusing. I apologize. Sometimes 1 and 2 are used for initial and final, sometimes I and F. So I'm just going to try to be consistent and use 2 and 1. Right. So U2 minus U1 is equal to negative of K2 minus K1, which is equal to K1 minus K2. From that we get the result K1 plus U1 is equal to K2 plus U2. Right. And this is the very important result which we know. This is called the principle of conservation of, it's actually the conservation of just mechanical energy, but we call it the conservation of energy nonetheless. Right. So the phrase I used right now was mechanical energy. That is just a terminology. Mechanical energy is just K plus U. It is the sum of the kinetic energy and the potential energy. You can have a very large number of types of energy. You can have thermal energy, you can have chemical energy. We will not deal with them right now. For our purposes, the two energies which are important are kinetic energy and potential energy, and the sum of them is the total mechanical energy. Right. So the result we've reached right now I'm just gonna write it again properly. These are the results we saw earlier. For a single particle, W equals K2 minus K1, and for a system of particles, W external plus W internal is equal to K2 minus K1. But what would we do? Let me write this again. But what is W internal? W internal is U1 minus U2, because U2 minus U1 was negative of W internal, right? And if we take W external to be 0, this is equal to K2 minus K1. I'm just deriving it from this result. This result implies this, right? Which means K1 plus U1 equals K2 plus U2. So the result is total mechanical energy of a system is constant if external forces do no work. This is the principle of conservation of mechanical energy, right? If you have a system of 20 particles and there is no external force, or rather another case we saw earlier was if the forces are always perpendicular to velocity, they don't do any work, right? So for whatever reason, if we have a system of a number of particles and the external forces are not doing any work, then the mechanical energy of the system will be constant, right? So let's take our familiar case M1 and M2. Let's say they have a force of attraction towards each other. Initially, let's say they are at rest, so they have no kinetic energy, right? They might have some potential energy. When they've come to this point, this M moves from this point to this point, and this M moves from this point to this point. The internal force will have done some work, right? But also their kinetic energy will have changed, right? So we see that the kinetic energy will have increased, and since the internal forces would have done the positive work, the potential energy would have decreased, right? So if the kinetic energy increases by 10 joules, the potential energy would have had to decrease by 10 joules, right? So we see we haven't done really anything new except some terminology. So we earlier knew work done by external plus internal forces is equal to change in kinetic energy, but we know that internal forces are not very easy to work with. They involve integrals, and so it's better to define something potential energy, which is the negative of the work done by internal forces, and from that we reach this result, right? Just a couple of other small points. There is no such thing as potential energy. Now, what do I mean by that? There is no real definition of a particular potential energy at a particular point. Remember, our definition of potential energy was U2 minus U1 is equal to minus W internal. That means we never ever define a potential energy. We only define a change in potential energy, right? So let's say this is the first particle, this is the second particle. The second particle could be either at this position or this or this or this. Let's say if the second particle is at this position, the potential energy is 10. At this position it's 11. At this position it's 12, 13 or 20, let's say, right? These are the potential energies at the 5 positions. So if I take an object from this point to this point, the change in potential energy is 1. That means the negative of the work done has to be 1. But there is no such thing as an initial potential energy, so we are free to choose a 0 anywhere we want. So if these were the potential energies, I could just as easily have chosen, I'll call this to be the point of 0 potential energy, right? But then the others are fixed. If this is 0, then this has to be 1, this has to be 2, this has to be 3, and this has to be 10, right? So we are free to choose the 0 of potential energy at any point we want, right? The change in potential energy is the only thing that matters. In fact, if ever you have a question in an examination which asks you what is the potential energy, you can be 100% sure that somewhere in the question they've given you a hint as to where to choose the 0 of potential energy, right? Because if they haven't and they ask you what is the potential energy, you could legitimately say, well, if I choose this position to be potential energy 0, then your potential energy is 36 joules. But if I choose this position to be 0, it's 35 joules. Right? So we are free to choose a 0 anywhere we want and everything else falls into place. Just a small example, we'll see gravitational potential energy in detail later on, but it's basically dependent on the height, right? So we could take this to be u is equal to 0, and let's say this becomes u is equal to 4, and this is u is equal to 15. Or what we wanted to do, if according to the convenience of the problem u is equal to 0 it was convenient to take this height as u is equal to 0, that's fine. That's fine. All that would have to happen was this would have to be equal to u is equal to minus 11, and this would have to be equal to u is equal to minus 15. I ask you, what is the potential energy at this point? You're going to say, hey, I can't tell you. It depends where your 0 is. If your 0 is at the top, then it's minus 11. But if your 0 is at this point, then it's 4. Right? So that's one important point. Secondly, let's see what we mean by work done by internal forces, right? It means integral I to f dot dr, right? So let's say this was the first particle, this was the second particle. The second particle moves from this initial position to this final position, right? The integral of f dot dr from I to f, the negative of it would be the change in potential energy, right? Now, a legitimate thing you could say was, if I took the object, the particle along this path, or along this path, or along this path, in all three cases, what if the work done is different? What if this integral has a different value? Well, in that case, we cannot define a potential energy, right? So we define forces into two categories: conservative forces and non-conservative forces, right? Conservative forces are those forces in which work done does not depend on the path taken. And obviously non-conservative forces are the other one, in which the work done depends on the path taken. So for conservative forces, integral I to f dot dr would be independent of the path we take, right? It ultimately would be a particular value, and so we can define a potential energy for these. U can be defined. But for non-conservative forces, we cannot define a potential energy, right? Now, let's say integral I to f dot dr is independent of path. That means I go along this path, it has a value 10, let's say. And I go along any path, it has a value 10. That means if I go along this path and I come back along this path, then this would give me a 10 and this would give me a minus 10, right? Because now the direction is opposite, so the limits have reversed. So the sum would be 0. Another way of saying the work done does not depend on path is, we could also say that work done during a round trip is 0. Right? So let's look at this in a little bit more detail. We did spring forces earlier, so let's take that. Let's say this is the point of natural length. I extend this object and then I compress it and it comes back to this point and then it comes back to the original point, right? What was the work done? We calculate the formula for work done. It was half k x1 squared minus half k x2 squared, where x1 and x2 were the extensions. Now we see that this is the initial extension, this is the final extension. It doesn't matter what the extension was between them. In other words, if initially x1 was 0 and finally x2 was 0, then the work done will be 0. So I could take an object from its natural length, I could extend it, then compress it, then extend it a little bit more, compress it, and finally allow it to come to its natural length. The net work done by the spring will be 0. When I'm extending, the spring does negative work, right? Because the displacement is towards the right, but the force by the spring is towards the left. In this direction, the spring will be doing positive work till here. Then it's doing negative work, positive work, negative work, positive work. Right, so the net work done by the spring is 0. So the force due to a spring is an example of a conservative force. right? And because it's an example of a conservative force, we can define a potential energy corresponding to it. So this is the work done. Now, an important thing to note is when we write this as work done is equal to this, in that case we are choosing this object as our system, and we are saying the work done on this object by the force of the spring. But if we want to calculate the potential energy of the spring, we need to take this combined thing as a system. That is this object plus this spring plus this wall it is attached to. If we take this combined thing as a system, now this kx, the force of the spring, is not an external force anymore. It becomes an internal force, and for internal forces potential energy can be defined. Right. So the work done in that case will exactly be the same. So this will be equal to u1 minus u2, right? Because u2 minus u1 was the negative of the work done. And you can match these two and you can see u equals half kx squared. This is the potential energy of a spring by virtue of its extension or compression. We can see it's positive regardless of whether it is extended or compressed. This u is taken when u is equal to 0 is taken at natural length. Meaning x equals 0. Right. If when x is equal to 0 we take u equal to 0, then if we extend or compress it, the potential energy in a spring will be half kx squared. Right. Let's look at a second type of force, the force due to gravity. We'll only look at gravity as a force equal to mg downwards. Right. We'll not take it as gm1 m2 by r square. That we'll do in detail when we get to gravitation. Right. So if the force is mg downwards, right, let's say this is the ground and this is equal to 5 and this is h is equal to 15. An object goes from this point to this point. Right. Now, if we take this particle to be the system, then gravity will be an external force, right? And we'll use the work energy theorem and say work done by gravity will be equal to change in kinetic energy. But energy of this gravitational force, we need to take this object plus the earth as a combined system. Now we'll assume that the earth doesn't move because it's very large, and even if it moves, it will be a tiny amount compared to this particle. Right. So the work done will be integral of mg dx. It is initially at 5, finally it is at 15. But since the displacement is upwards and mg is downwards, we have to attach a minus sign. Right. So this gives me minus 10 mg. This is the work done by gravity. Right. Or actually it would be better if we take it as h1 and h2 for now. So instead of 10 mg and instead of 5 and 15, let's take it as h1 and h2. In that case, this would be minus mg h2 minus h1. Right. So this is the work done. I apologize. The work done is minus mg times h2 minus h1, right, which is equal to mg times h1 minus h2, which is equal to u1 minus u2. The work done by internal force is equal to u1 minus u2, which gives me u equals mgh. This is the potential energy of gravitational force. And we know if we take this object upwards and then we bring it down, the net work done by gravity will be 0. So work done is a conservative force. Right, and the potential energy is mgh. Also, we could take any potential energy to be 0. For example, and it's also, since mg is constant in this case, it is sort of proportional to height. So we could take this h is equal to 5 and this h is equal to 15. Or I could solve the problem simply as saying this is h is equal to 0. But now this h can't be 15, right? Now this h has to be 10. And then again h2 minus h1 would give me the same answer. So this is what I mean when I say we can take any point to be the 0 of potential energy and everything else will fall into place. There is one point which we'll need to nail down and everything else will fall into place. Right. So we've talked about conservative forces a lot. Let's talk for once about non-conservative forces. Friction is an example of a non-conservative force. First of all, we can simply see, let's say the plane of this monitor in which you are seeing this video is a surface. And this is an initial position and this is the final position. If I take an object like this along the shortest path, friction will do the minimum amount of work. If I take it along a very long path, friction will do a large amount of work. And if I push an object and it moves along a circle and comes back, its speed is going to be less than the speed with which I pushed it, right? Because friction will reduce the speed. So the work done by friction in a round trip is not zero. So friction is an example of a non-conservative force. And so you will never ever hear the term potential energy of friction. Right? This completes work and energy. In the next lecture, we'll see some examples on how to solve problems. Thank you.